All right, we talked about first half of the chapter 5, energy from combustion. So let me see whether I can review some of that. It's kind of slow. And we also talk about energy measured in joules and calories, heat energy. Measuring energy changes. We also talked about how energy is produced in combustion reaction. We use fossil fuels to produce electricity. So today we're going to start with power plant, section 5.7, and how fossil fuels are used in producing electricity. So I'm going to go to that slide. How we produce energy from fuels follow certain thermodynamics, follow certain laws of thermodynamics. One of the laws of thermodynamics important to energy transfer is first law of thermodynamics. It is a statement that energy is neither created nor destroyed. That means energy is already here. Amount of energy is already here. We are not creating or destroying it. We are only transforming it to another form. So that's one of the principles of thermodynamics, like conservation of mass in chemical reaction. In thermodynamics, first law is energy is neither created nor destroyed. Now there's also thermodynamics law called second law of thermodynamics. It talks about entropy. Entropy is related to randomness or the disorder in the universe, in the things we deal in the universe. So one thing this statement, second law of thermodynamics says is entropy of the universe is increasing. That means when something takes place, it happens so that disorder is increased. So this is related to heat production. When you produce heat, it also produces disorder. It increases the entropy of the universe. That excess heat released in combustion reactions goes to increasing entropy of the universe, the weather, the thunderstorms, hurricanes. It's destruction. So it's one of the principles of the thermodynamics, entropy or the destruction of the universe should be increasing. In one part, if one part of the universe is becoming organized or orderly, then another part has to become more disorderly to balance that law of thermodynamics. So we're going to mainly talk on first law of thermodynamics, okay? And second law is only used as dissipation of heat energy and producing a lot of things in the environment. If you look at the diagram given below, where fossil fuel is burned, in the diagram right here, boiler, the steam is produced during the production of electricity. That boiler steam is passed down to a turbine. Then turbines run a motor, and turbine turns the generator coil, mechanical energy. So that coil changing in magnetic fields produce electricity, and electricity is sent to populated area, to a city or where people live. Now, after steam passed through turbine, we send it to a condenser, cooler. Steam is condensed back to water and sent back to boiler to be reheated. So condenser cools steam using body of water on a pond or some reservoir. So recirculating that water. So there's some of the heat is given out to environment when you heat. So it's a complex process. So there are a lot of places where we can release a lot of heat energy. Not 100% of the energy produced from heat is not converted to electricity. So we're going to talk about the efficiency of this conversion in the next slide. So summarizing, in the boiler, potential energy of the fuel is released as heat in the burner. The burner heats up water and produces steam where kinetic energy is higher temperature also. Then it's passed on to turbine. Turbine turns kinetic energy, mechanical energy. Then mechanical energy of the turbine converts it to electricity through the generator. So electricity is passed on to where it is used. So this is what happening when electricity is produced. The electric power plant cannot completely convert one type of energy into another. That means heat cannot be converted to 100%, converted to electricity. Only part of it is converted. So electric energy produced and heat from the fuel. Normally, if it is 1-to-1, then all the heat is converted to electricity. But heat produced from fuel is not equal to electricity generated by the motors. So net efficiency of this conversion is given as power plant efficiency, electric energy produced divided by heat from fuel burn times 100. So some of the energy is transferred into useless heat. That's where the second law of thermodynamics comes in. It agrees with the second law. I mean, if electricity production from heat is thermodynamically feasible, the entropy of the universe has to increase. So heat wasted or released create that. In the environment, there are more effects. Heat in the environment causes climate change and etc. They are increasing the entropy of the universe. In general, the higher the temperature in the steam and the condenser, lower the temperature in the condenser, the more efficient the power plant is. So therefore, we have to produce heat at high temperature, steam at high temperature, it's 100 degrees. The cooling should be done at lowest temperature. So to make it more efficient. Calculated maximum efficiency, the calculated one that we, based on factors we know, is the function of highest and lowest temperatures needed to make steam and condense it. This is the temperature difference between heat production and the condenser. So burner has to be running at high temperature. Condenser has to be running at lowest possible temperature. The overall energy is the product of efficiency in terms of many things. Theoretically, we should be able to produce 55 to 65% of heat energy from burning. Boiler efficiency is 90%. Turbine efficiency is 75%. Generator, the mechanical energy, conversion of kinetic energy to mechanical energy is 75%. Heat energy to kinetic energy is 90%. Mechanical energy to electricity is 95%. But when you have three things like that, it's going to be decided by multiplication of all these. So you cannot, maximum you can get about is 70. So theoretically, considering many factors, is about 55 to 65%. The transmission is efficient, 90%. So overall, really what we see is 32 to 37, 37.5. The maximum we can get is 37.5. Those are all theoretical on the top, calculated. But in reality, heat burn, only 32% of the heat burn from fossil fuels is converted to electricity. So we are talking about the same thing here, efficiency of this setup: boiler, condenser, turbine, and motor, generator. So that's what we think about it. Now we're going to turn the topic to source of energy, fuel source. The coal was ancient. Ancient means first we discovered coal before petroleum. Before coal was wood. Wood was the kind of oldest ancient fossil fuel. Then it's replaced by coal. Up until 1960, wood was the major source of energy. Then coal took over. This diagram also started around 1992 here. So up to about 1960, wood was the major source. Today, 92% of the coal used is used to produce electricity, to generate electricity. 92%. There are a lot of coal burning power plants. We burn the coal and make the steam and generate the electricity. If you look at the diagram here, there are regions of countries who use coal. They are in million tons of equivalent to oil. So if you look at this, in 1992, these different regions are different countries. The bottom is North America. That includes Canada, USA, and South and Central America is green. South and dark green. Europe is light green. Russian Federation, including all the breakaway countries from Federation, Soviet Union of Russia, thus purple. Middle East is red on top of that. Asia and Africa is blue. Then Asia Pacific, Asia, including China and other Asian countries. Look at the majority of them are burning coal. Right now, they are increasing. Gone down a little bit in 2019, but it is a lot of tons of coal, million tons of coal. So China has a lot of coal resources, so they use most of the coal in the world. To cut down coal burning is difficult because we had to ask developing country to stop burning coal. So we're going to talk about that in the next few slides. Now, we need to do coal calculation about heat production from coal. Coal is a compound with formula C135H96O9 and nitrogen and sulfur. When it burns, it produces carbon dioxide, nitric oxide, nitrogen dioxide, and sulfur dioxide. Therefore, it pollutes as we burn coal. If we didn't treat to remove sulfur, it also produces nitrogen dioxide. A typical power plant uses about 1.5 million tons of coal in a year, 1.5 million coal tons. So we had to get an awareness how many tons of carbon dioxide, and how much heat is produced from burning coal. Compute the amount of energy released by burning this mass of coal. Assume 30 kilojoules per gram of coal is released for that formula. Useful conversion factors, tons to pounds and pounds to grams. So we need to do that. And quantity, calculate the mass of carbon. Then the C is carbon. In A, we have to calculate mass of carbon in tons. And C, we has complete combustion of what the mass of carbon dioxide produced during the complete combustion of coal. So if you have a problem like that, I know it is hard, but let me show you how I worked it out. So this is kind of a research work you can do with data from different places and solving a problem. You have to first get the chemical equation, assuming a mole ratio of coal to carbon dioxide is 135. Let's see whether we can do it. So I'm starting to calculate here. Molar mass of coal is 190, I cannot see that, and carbon dioxide is 44 and carbon is 12 molar mass. That means molar mass is producing 1 molar mass is producing 135 carbon dioxide molecules. Let me get this little bit worked out. This is kind of I couldn't see the slide. Okay, let me go back. Still it's not showing up. Okay, hold on a second. Okay, can you hear me that I was talking about extracting more oil from sandstone, passing carbon dioxide into depleted oil wells and pushing out methane and extra oil, crude oil from the sandstone. That's one of the process called squeezing oil from rocks. Okay. Can you hear me now?
Yes, we can hear you.
Okay, all right. Except I got stuck here. Okay. The fracking is another process. You heard about, how many of you heard about fracking? Fracking is used to obtain natural gas. Natural gas also, as it gets depleted in the hard rock formation, shale, trapped in the shale rocks. It could be extracted by passing, drilling to the bottom, the rock layer where the natural gas is, and sending water and sand, heated up water and sand into the bottom. It opens up the it produces cracks in the rock layer where the natural gas is trapped. So then it pushes out whatever oil and natural gas up to the top under the high pressure of steam. So this process is controversial. How many of you heard about fracking that can contaminate groundwater with natural gas? Fracking fluid containing variety of substances is injected under pressure to create cracks into which natural gas and oil can flow. So fracking is talked about in political discussion about environmentalists. Politicians wanted to give commercial gas industries then green light to go ahead and do whatever you want to do, make money, make jobs. There are a lot of issues with that. Highly controversial. Questions about water quality, destabilized rocks that lead to earthquakes, seismic activity. So if you need to look up this is a good topic that if you like to see more details. Now we are going to talk about crude oil. That's the oil that we pump out of oil wells. Natural gas is the mainly methane, 95% methane that is trapped inside rocks on Earth. So when you drill a well, you can have natural gas coming out. You can have crude oil plus natural gas. Normally, crude oil and natural gas comes together, so you have to separate it out. Some places, natural gas only comes out, no oil, depending on the deposits. Crude oil is a mixture of several thousand compounds. The majority being 5 carbon to 12 carbon atom per molecule. Alkanes are the hydrocarbons with single carbon-carbon and carbon-hydrogen double single bond, alkanes. Alkenes have double bonds. They are a little more reactive than hydrocarbons. Alkynes like acetylene at least have 1 triple bond. So crude oil is a mixture of all these. Hydrocarbon use prefixes to identify the compound. We use that mother eats peanut butter, remember ethane, methane, ethane, propane, butane, pentane, hexane, heptane, octane for natural hydrocarbons. So you use prefixes to denote the carbon number. Methanol is an alcohol with 1 carbon atom. Ethanol is alcohol with OH group with is called alcohol with 2 carbon atom. Propanol, butanol, or methane, hydrocarbon, ethane, propane. If it is unsaturated ethene is ethylene is the common name, ethine. Ethine is YN is triple bond. So you use naming. N for the hydrocarbons, ene ending for the suffix for the methane, ethene, ethine, Ethine is a triple bond acetylene. So if you look at the different hydrocarbons, these are saturated hydrocarbon or alkanes. As the temperature, as the carbon number goes up, can you see that melting point, boiling point increases, boiling points. It starts with negative, then go low on negative, that is increasing, then when positive is increasing. Negative to positive is an increase. So it depends on the carbon number. The last one we talk about is octane, N-octane. These are all N, normal. N means normal octane. N means straight chain. So these are the condensed formula on the last column, condensed formula, structural formula. So we talked about different kind of formulas. Methane, ethane, propane, butane, pentane, hexane, heptane, octane. So boiling point of these hydrocarbons become higher as they increase the carbon number. Carbon number is related to electrons. More carbon and hydrogen the hydrocarbon has, it has more electrons. The volatility is a measure of how low melting point is. Methane is mostly volatile. Volatile means it's become a gas quickly. It's a gas. Natural gas is a gas because high volatile. Ethane is next. Propane is liquid in a gas tank. Butane is a liquid in a gas lighter. Then pentane to octane are gasoline. That's in your car or gas pump, gasoline. So they all depend on the volatility, depend on intermolecular force known as London dispersion force. The hydrocarbons are non-polar molecules. Intermolecular force between them is London dispersion. The more electrons it has, the molecule can fluctuate electron clouds in the molecule and produce instantaneous dipoles. On the right bottom, London dispersion is an interaction, temporary interaction created between non-polar molecules. More the hydrocarbon, carbon number and hydrogen numbers, the more the London dispersion force is. It is proportional to the number of electrons. Methane has very little electrons. As butane, pentane, hexane, as the carbon and hydrogen number increase, they become high melting, high boiling. Boiling point, the stronger the force, the higher the boiling point. More carbon and hydrogen is in the hydrocarbon, the boiling point increase. So this property of volatility is used to separate crude oil mixture into fractions. In an oil refinery, there's a distillation column. That's where the tall columns where the gas is coming out or burning flame here. These are distillation columns. Then after we distill crude oil and we get the fractions of crude oils, different fraction, we're going to talk about that, and store them in storage tanks. and send them to market. So oil refineries has distillation columns, stall columns. Basically what takes place in a distillery is in one of the distillery columns, that boiler at the bottom, the crude oil is pumped into a tank. Crude oil, what is it called? Boiler. Is sent into the boiler, heated it up. Then the gas produced is sent into the distillation column. The more volatile compounds end up on the top layers. Less volatile, there are apartments or stacks of on the distillation column. So hydrocarbons get separated into different fractions. If you look at this diagram little bigger, the bottom has the carbon 16 to 20. These are waxes, high boiling fractions. 13 to 18, little more volatile. I'm trying to get it increase in the size here. The bottom one is industrial fuel, lubricants. So there are how many sections you have? 1, 2, 3, 4, 5, 6. The top layer has the refinery gases that are like methane, volatile compounds. So after refinery gases, we have carbon 1 to 4 up to butane. Then second plate has carbon 5 to 13. So they can be taken out from the sideways. It shows refinery gases. Gasoline comes out of this carbon C1 to C4. Jet fuel C12 to C16. Diesel C14 to C16. They come out of these lines and you can get those things collected. We also use a reformer on the gasoline. A reformer is a process, place where the gasoline is converted to branch alkanes. I'm going to talk about that. Also, on the bottom, there's a coker. It is a place where high boiling fractions were heated up and break into smaller fragments used as a industrial fuel and lubricant. Then also C10 to 20, C15 to C18 fractions are sent into a cracker. It breaks up and goes up to the gasoline. So cracking process produce more gasoline. So that's how we distill crude oil. Distillation is used to separate crude oil into its components. The boiler heats the oil, vaporizing most of it. Vapor condenses at different temperatures on distillation tower and are collected. Once we separate the crude oil, if you use 1 barrel of crude oil, that's 42 gallons, about 87 of each barrel is used for transportation and heating. Rest is for lubricant and other asphalt and industrial fuel. So out of 42 gallons, 20 gallons are gasoline. The major component in crude oil is gasoline. Diesel also produce about 12 gallons. Jet fuel is 4 gallons. Heavy duty fuel oil, lubricant, liquefied petroleum gas. These are the light ones, small molecule, liquid refinery gas, other products, 6 gallons. So mostly we get diesel and gasoline. The cracking is in the diagram. In the bottom, we crack large carbon-containing fragments, C16 to pentane and C11. So pentane can go to gasoline, and some of them are going to go to jet fuels and this side. Cracking is a process where you heat the fraction to high temperature and breaks up the hydrocarbon into two pieces. You use a catalyst. Catalysts are substances that help in the increase the rate of cracking here, the rate of the breaking up. There are specific catalysts called catalytic cracking catalysts. Reforming is done on the top in the distillation column on the top. Catalytic reforming rearrange the atoms in a molecule, usually linear molecules, and produce more branch ones. The bottom one has linear chain. If you reform it on the right side, the bottom, there's a branch alkane. So catalytic reforming produces linear alkane to branch alkanes. So there are a lot of other types of structures are shown. So first 4 on the top diagram are in here linear. The bottom one is the left branch, and the right one, there are 2 of them on the right here. Let me move them. These 2 on the middle diagram. On the left, there's a linear. So catalytic reforming produces more isomers. Isomers is same molecular formula, different arrangement of atoms. So branch alkane, linear alkane is converted to the same number of carbon atoms, branch alkane. It has the same number of formula, carbon atoms and hydrogen formula, chemical formula, but different arrangement. So reforming produce branch alkanes. Branch alkanes are useful in gasoline, like isooctane is a branch alkane. Molecules with linear structures have a stronger attraction. Linear hydrocarbon with linear chains have stronger, higher boiling points. A branch alkane known as isooctane. Isooctane is the one down here. This is, I think, octane. Isooctane on the bottom. The linear octane, N-octane is on the right. So octane is used, isooctane is used as an additive to the gasoline to prevent knocking. Branch alkanes burn smoothly and let the engines run without vibration. So gasoline that contain octane are higher fuel consumption and less energy damage. So this engine knocking is prevented by isooctane. Therefore, gasoline with octane rating, high isooctane rating, are good for engines. Octane rating was developed to indicate the gasoline quality related to knocking. Knocking is when you have more linear hydrocarbons. The gasoline burns unevenly, so therefore it is causing knocking. Knocking means vibrations and engines vibrate. So you can read this about in the chemistry of petrol. So compounds, these are the ones that you use to increase the octane rating. If you have N-octane, it's bad. N-octane is linear octane. Knocking is worse. Even negative octane number means bad. N-heptane, it doesn't affect that much. No, it's still the same knocking. Isooctane, 100% knocking is reduced. Methanol also, adding methanol also reduce 109. Methanol is not adding to gasoline because it can damage engine parts. So ethanol also 109. Therefore, ethanol is an additive that we use to increase the octane rating. MTB, methyl tertiary butyl ether, has the best octane rating. So either we can add ethanol or MTB to increase the octane rating. So the gasoline that we use ethanol or MTB. We used tetraethyl lead long time ago. It's called leaded fuel. Right now we pump say unleaded. Unleaded means there's no tetraethyl lead. Because we used tetraethyl lead, there were a lot of lead poisoning around the highways and gas stations where the vehicles are found running around. So around highways, the amount of lead increased. So we found out and we stopped using tetraethyl lead. So it's like a story about freon. Freon found to be causing ozone layer destruction. Tetraethyl lead added to gasoline to increase the octane rating cause lead poisoning. Now we are mainly using these two, MTB or ethanol. Remember we talked about catalyst for cracking and reforming. Catalyst is a general name in the chemistry that's used to lower the activation energy for a reaction. So this is in the diagram, the green line here, reactants go into products. normally follow that green line. The higher the hump here, more temperature you need to get the reaction done. When catalyst is used, it reduces the activation energy. Therefore, reaction take place at lower temperature. For example, to burn glucose, we have to use high temperature. But within biological system, using catalyst, it reduces the temperature. It normally takes place in lower temperature and faster speed because enzymes are used. Enzymes are biological catalysts. Enzymes are molecules that increase the rate of chemical reaction that take place in living organisms. Catalyst causes the reaction to proceed faster than the uncatalyzed reaction. Uncatalyzed is in green. Blue pathway is the catalyzed reaction, lower activation energy. The Fischer-Tropsch catalyst, where the coal is converted to gasoline, are one of the examples of catalysts that does coal to gasoline conversion at low temperature. Another catalyst is reforming catalyst, cracking catalyst, etc. Ethanol is, as you can see, is the additive for gasoline. It's mainly derived from biological sources such as trees, grass, and agricultural crops like corn. Ethanol is a biofuel produced from sources from living plant or animal sources. Ethanol has a functional group called OH. And the diagram, the red ball is oxygen and attached to hydrogen. It's like I call this ethanol molecule a little doggy. The dog's head is red. Tail is on the second carbon atom on the next carbon atom. I used to joke around with this. When you drink a doggy-like molecule, you also become a doggy. So you become a puppy and wag your tail and all that stuff when you get drunk. To obtain ethanol from corn, a soup of corn kernels and water is mixed with enzymes. So glucose is fermented. Corn has glucose material. Sweet corns, you can see it says glucose. And the starch to glucose, fermentation. So glucose is converted to, starch is converted to glucose. Glucose is fermented. Glucose is converted to ethanol. Ethanol also can come from plant containing not only food products, it could come from cellulose material, which are not used as food. There's a big deal about trying to produce ethanol from celluloid plant material like trees, tree trunks. We cannot eat them. So cellulose, if that can be produced to make alcohol, that is a good thing. So cellulose ethanol is a biofuel from non-food. List the 3 desirable characteristics of source of cellulosic ethanol, such as wood chips and switchgrass. So there are work going on, research going on in this area to produce. Now, if you look at oxygenated fuel, ethanol is an oxygenated fuel. It has lower amount of heat burned than hydrocarbon found in gasoline. Remember that diagram we had, the more oxygen hydrocarbon has, like glucose, ethanol, the heat given out during burning one gram of that material is reduced. So therefore, adding ethanol reduces heat mileage we can have. We can go in a gallon of gasoline added ethanol. If a gas station had more than 10%, some they do, then you have lower gas mileage. Octane releases much more energy than ethanol. Car engines cannot run on ethanol by itself. So gasoline blends are used, which often contain 10% ethanol. This is to increase the octane value too. Super fuel, you get regular and a super. Super has more isooctane than ethanol. Therefore, it runs smoothly, give little more gas mileage. This increase in octane rating of the fuel and reduces emission that produces ground level ozone. Biodiesel is another biofuel produced from vegetable oil. Vegetable oil is triglycerides, that in the diagram on the left side, triglyceride. Glycerol molecule with 3 fatty acids. When you use methanol and sodium hydroxide, it produces biodiesel. It's a methyl esters of fatty acid, and glycerol is released. So biodiesel is produced from used vegetable oil, triglyceride, reacting with sodium hydroxide and methanol to produce biodiesel. Produced from fats and oils and waste cooking oil, which are found in waste cooking oil. Biodiesel molecules contain a hydrocarbon chain of 16 to 20. Diesel also contain carbon number of 16 to 20. The chains usually contain at least one double bond. Some of the biodiesel chains contain double bonds. Biodiesel molecules also contain oxygen as a ester functional group. Ester functional group is carboxylic acid with methyl as an ester. Glycerol is produced as a byproduct, which can be used in its own application, converted to other alcohol. Glycerol has many other uses. So when you produce biodiesel from vegetable oil, you produce glycerol. Glycerol can be used in food additives or converted into other alcohol. So to produce biodiesel, you need ethanol, you need sodium hydroxide, and you can produce biodiesel. Biodiesel, let's see what's here. Heat of combustion of biodiesel is less than heat of combustion of diesel. Why? Because it has oxygen, okay? Oxygen functional groups. revisit the structural formula of a biodiesel molecule. It has oxygen. Would you predict that the heat release per grams of biodiesel burn is higher or lower than that of octane? I think it's higher than octane because there are 16 to 20 carbon atoms, even though oxygen lowers compared to biodiesel. Biodiesel have less energy produced, but diesel produce more than octane. Octane is like in a gasoline. Do you know diesel itself has more heat produced? Why we use diesel for heavy vehicles? Because they need more energy to run. They give better gas mileage using a diesel car or something. So biodiesel release more energy than octane. So we see figure 6.5, see the values of different fuels. We compared hydrocarbons, oxygenated hydrocarbons, and glucose there. If instead of the comparison made with basis of 1 mole of biodiesel versus 1 mole of octane, still 1 mole of octane can contain only 8 carbon atoms, less bonds. But 1 mole of biodiesel contains many carbon bonds that could be oxidized to produce carbon dioxide and water. Therefore, it produces more heat. It is more useful to make comparison per grams of fuel rather than per mole of fuel, because we usually do the business with not with moles. Grams are the ones that we can measure. For chemistry, to be precise, we can use moles, but when you're doing a practical application, we normally use per gram for comparison. So we want to summarize this. Fossil fuel produce 79.5% of our energy. So nuclear produce about 2.2, 18% from renewables. So once the fossil fuel is gone, we are left with renewables and nuclear power. So we have to increase alternative renewables. All renewables are traditional and modern. Traditional is biomass, burning wood and etc. Modern renewables are like geothermal, solar heat, hydropower, wind, solar, biomass, geothermal power, and biofuels. Biofuels include ethanol, biodiesel. Hydropower include water cycle of the water is trapped in a reservoir, could be used to generate electricity. Biomass, geothermal, solar power. So this we're going to look into a little later in more detail. Let's summarize this chapter with ethical principles of biofuels. Biofuels developed should not be at the expense of people's essential rights, including access to sufficient food and water, health rights, work rights, and land entitlement. So there are issues involved with biodiesel. So big corporations could interfere, and governments can give subsidies and force unreasonable lower price for biodiesel. biofuels. Biofuels should be environmentally sustainable because it should produce no effect on the environment, neutral effect. Biofuels should contribute to the net reduction of total greenhouse gas emissions and not damage global climate. Biofuels should be developed in accordance with trade principles that are fair and recognize the rights of people to just reward, including labor rights. It's like intellectual property rights. It's like the first one. Cost and benefits of biofuels should be distributed in an equitable way. If the first 5 principles are respected, so this is the guideline for using and producing biofuel. Then depending on the additional key consideration, there's a duty to develop such biofuel. These additional key considerations are absolute cost, alternative energy sources, opportunity cost, the existing degrees of uncertainty, irreversibility, degree of participation, and the notion of proportionate governance. So biodiesel is a controversial issue still. Are biofuels are really sustainable? Biofuels are potentially more carbon neutral since they were derived from modern crops and grass and trees. They recycle carbon dioxide and absorb and recycle. Carbon release on the combustion is partially offset by the carbon these plants once absorbed by photosynthesis. Hard to gauge the net reduction of carbon dioxide emission from biofuels. Direct and indirect changes in the use of land. Growing bio plants to produce biofuel change the land. Waste product from biofuel also create a problem. How much energy was required to produce the biodiesel, including that use in plant and harvest crop produce fertilizers and water the crop. So biodiesel is good to recycle vegetable waste and etc. But it shouldn't be the main thing that we rely on. So we finished chapter 5 and we done with combustion and certain aspects of fossil fuels. Okay, I'm going to stop the class today. We will meet on next Wednesday. All right. Can you guys hear me?